So, let's take a look at number 41. Oh, we did 41. That was the CH3 at H2. That whole last thing I just did there was number 41. So that's how you do number 41. 43. We are asked to find the KB for the following situation. We have a compound, HOC2H4 NH2. Now, because we've studied organic chemistry, we know right away that this is a base because that's an amine. We ignore all the other nonsense in front of it. But we also know that the concentration of this is 0.15 molar. And we are told that the pH of this solution is 11.34. Well, see, that tells us it's a base because it's greater than 7. So, we need to hydrolyze that, turn it into an Arrhenius base by making this a 3 and putting an OH on the end. And we added water. So, let's write this reaction down. HOC2H4 NH3OH. Double arrow because it's a weak base. Hydroxide comes off. Plus HOC2H4 NH3 positive. Okay? Now, we also know that we have a 0.15 molar here. So we're going to do a little mini ice state. We're going to lose X here, or we're going to gain X here, and we're going to gain X here. So our KB is equal to X squared over 0.15 minus X. But here is the big difference. The fact that the OH now is the X instead of the H like we had in the acids for the Ka. So we know that the concentration of hydroxide is going to be our X. Okay? Now, we don't know the Kb, but we kind of know this because of this piece of information right here. Since we're dealing with OH, we don't want POH, we want pH. I mean, we don't want pH, we want POH. So we can find POH because we said earlier that pH plus POH equals 14. Therefore, 14 minus pH equals POH. So that's 14 minus 11.34. So POH equals 2.66. So what does that tell us? Well, we can find the concentration of OH because we know that the POH is the negative exponent of 10. That's what P means, negative exponent or negative log of 10 of the OH concentration. So this is going to be 10 to the negative 2.66. It's the negative exponent of 10. So we punch that into our calculators, and we find that we get 2.19 times 10 to the negative 3 moles per liter is our hydroxide concentration. And that is our X. It's the same for this right here, same value. So we plug in for X, that number there, and that number there. So KB equals 2.19 times 10 to the negative 3 squared, divided by 0.15 minus 2.19 times 10 to the negative 3. We just punch that straight into our calculators. Hit enter, and the answer you're going to get for that is 3.24 times 10 to the negative 5. And there's your value for your Kb for that substance, which is not in the book, but we know how to find it once we give it the proper information, which we did. Number 45. We're given here a 0.065 molar solution of methylamine. And like I said, we know that the Kb in that chart on page 736 is 4.4 times 10 to the negative 4. And we want to know what is the hydroxide concentration for this, and we want to know what is the pH. Okay, so what we're going to do here is we're going to hydrolyze that thing. So we're going to add a hydrogen here, make that a 3, and add an OH on there. Double arrow, OH negative, plus CH3, NH3 positive. Okay? And we know that this is 0.065, and we're going to lose X of this, and we're going to gain X here, and we're going to gain X here. So the Kb, which is this right here, is going to be equal to X squared over 0.065 minus X. X times X over 0.065 minus X. Now we're going to do a little quadratic equation here, a little quad form. Alright, so we got to get rid of this, so we multiply both sides by 0.065 minus X. Okay, and then we get for that negative X squared. I'm sorry, we get X squared over here, and we get 2.86, that's a 2, times 10 to the negative 5th, minus 4.4 times 10 to the negative 4, X. Now we want to make a quadratic equation out of that, so we're going to add a negative X squared, rearrange this so that X squared is first, and then X, and then no X. And we get negative X squared minus 4.4 times 10 to the negative 4x plus 2.86 times 10 to the negative 5th equals 0. Now hit quad form. A is negative 1, B is negative 4.4, E negative 4, and C is 2.86, E negative 5. You get two answers. One positive answer that you should get for that is 5.13 times 10 to the negative 3rd moles per liter. What is X? Hydroxide. So we've answered that question right there. Next question is, what's the pH? Well, in order to do that, we got to find POH first. So POH we got to find is 10 to the it's the negative log, sorry, went the wrong direction. Negative log of 5.13 times 10 to the negative 3rd. Punch that into your calculator, and you get 2.29. Now we can find pH by taking 14 minus 2.29, and we get 11.71, and there is our second of the two answers. Okay? All right. We're going to take a look now at 47. And we're going to answer questions here. Is water going to be able to dissolve these compounds or hydrolyze them? Are they going to be hydrolyzed by water? If so, why? And if not, why not? Okay? So let's take a look at A, which is I negative. Now, this is a Bronsted-Lowry base. It is the, actually, I should be a little bit more definitive than that. It is a Lewis base, but it is also considered a Brunstad-Lowry base. You can have both, just like Brunstad-Lowry and Arrhenius can have the same semi-definition of acid and base. Why? Well, we're going to add water to this. And again, when we use water, we don't think of it as H2O, we think of it as hydrogen hydroxide. Now this is a single displacement reaction. And we take a look at this. You got positive here, you got negative here. So the iodide here is going to kick out the hydroxide. And the hydroxide then is going to be by itself. So you get hydroxide plus HI. So the question is this a legitimate hydrolyzation reaction? And the answer is no, it's not. Why? Because this is a strong acid. What happens when a strong acid is in water? It breaks apart 100%. It's never going to produce that compound. So this is not going to be hydrolyzed. It has to produce a weak acid because that's going to stay intact once it's formed. Let's take a look at part B. In part B, this one drives me crazy. I can always tell when inorganic chemists write textbooks because they write goofy things like this. This is supposed to be the formate ion, which is HCOO negative. But I think sometimes they worry about students getting all crazy about this and say, oh, that's an acid because the H is in front. But wait, it's a base because, well, I don't understand. Well, that's because, organic chemistry happens much later on in the textbook. We kind of jumped ahead. This is the formate ion. We're going to add water to that. Again, hydrogen hydroxide. Hydroxide is negative. This is going to kick that out. The hydrogen is going to join with this. So we've got hydroxide plus HCOOH. Now, is formic acid one of the 7 strong acids I gave you? The answer is no. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric acids. That's not one of them. So this is a weak acid. So yes, this will be hydrolyzed as written. Okay? Your assignment? Page 762, 42 through 48 even. Have fun!